Vucicevic. Stephen?
Hello, everyone. I'm going to start out our little session as doing the sort of little intro. And then the technical aspect, I'm going to hand over to Mirko. So I won't get to talk much, which is nice. But I still get to entertain you for a little bit. So since we've already been introduced, I won't cover our names again. Mirko and Stephen here. So Mirko does science computing for the Faculty of Science. He does research support. Basically provides support to researchers, and part of that's looking at sort of clustered type environments. His role is really to seek out and explore new ideas. I've heard that somewhere before. And my role is I work for the central group, which is called IST, Information Systems and Technology. I'm the liaison to the Faculty of Science. So I get to hang out in science and I get to ask questions. That's a great role about being a consultant. I actually don't have to do any work. I just say, so why do you want to do that? So that's my main role, and that's how we got here. The backstory is right now, we're in the process of sort of using this as a great idea. So I call it imaginationware. So it hasn't been quite implemented. It is a lot of really good ideas, a lot of research at this point. But it's just sort of looking at the problem of what happens when you have a really big lab, you're trying to do a teaching environment, but you've got all these resources invested in that room. And that room really gets underutilized in a lot of ways because the teaching environment quite often doesn't challenge that hardware, but you need it responsive enough so it's not lagging. And then you have all these hours where it just doesn't do anything. So in sort of doing my intro here, we're going to cover that backstory a little bit more as I go along. We'll talk a little bit about the lab, so I'll set that up. We'll talk a little bit about what the idea is, and then gathering pieces is Mirko. So the lab itself, as I mentioned, is 120 computers. It's actually set up as 60 desktops and 60 laptops, which is a little bit odd configuration. One of the reasons for that, the laptops being there, is simply space. So it's a very similar layout to this lab. So the way when you put desktops on it, it gets really crowded, especially when you try to throw that CPU underneath. So the laptop solves that nicely if every other workstation is the laptop, of providing that little bit extra leg room for students. It's not so great for actually room for typing. So that's one of the drawbacks for the laptops. Typically it's used for teaching, as I mentioned. So it's only busy really Monday to Friday. And there's all these other hours in the evening and on the weekend where it sits there and does nothing. So a lot of computers now are multi-processor. So really you're looking at, if every machine had 4 processors in that room, you're looking at 480 processors. So what were the issues in that lab? Well, basically it's Windows, and I could probably stop my sort of, these are the issues. Windows, it's a bit of a challenge when you're trying to use it with multi-users. We all know that. Windows constantly needs to be patched. The applications need to be patched. So there's constant updating, but you're a teaching environment, so you want to maintain its stability as well. So it's finding that trade-off. Again, talking about the processing power, and that comes up again and again in our discussions. That sort of, well, what do we do with this? We spent all this money, now it's sitting there. So how do we optimize that? And once you built the lab, it's static. So if a faculty member all of a sudden has a really great idea in the middle of the term, or a student has this really cool project that they just want to try something, how do you let them have resources on that workstation without messing things up? So what if someone wants a temporary app? We're all of a sudden come up with this new concept, something's big in technology. Teaching should be responsive to the moment, not to what happened 6 months ago. So just to give you a quick visual, that's the desktop. That's sort of the way the configuration is. That's the laptop, really nothing exciting. And so that's the lab with 120 computers. In many ways, the way we build labs now, they're basically really fancy server rooms because they got a lot of cooling in there. They've got a lot of networking. They've got a lot of other devices in there. So you can actually cut off this room from the rest of the environment and have it self-contained. In some ways, it's the entire computer. And so that's where we sort of go. The first question always is, well, why don't you just virtualize the applications? Isn't that the way we're supposed to be going? We're going to do bring your own device. We're going to take the applications, we'll put them up over here in the cloud somewhere, students will get to it. The problem is certain applications, the licensing doesn't work that way. There's a one-to-one still between the hardware and that application. Even Microsoft makes that difficult. There are ways of getting around that, but some of the teaching tools that we need to provide to students, we're still limited that way. So then the next question is, well, what if you disconnect the hardware and the software? What if you sort of virtualize or abstract that hardware layer? So now that hardware is just this big device, you put it all together, and then you do whatever the heck you want with the software on it. And so that's what we're looking at, basically, is sort of taking the entire sort of lab, thinking of it as one big piece of hardware, and doing a whole bunch of virtuals on it, and then swapping those virtuals. So the way I think of it is oven and cake. So right now, the way we do computers, the hardware, it's the oven. Our operating system is the cake. When we bake that cake, we throw it in that oven, and then we leave it there, and we expect people to use it within a month, which seems a bit of a silly way. You can only do one cake. You can't eat that cake, and you don't want people touching it. Whereas if you abstract that hardware layer, you can do as many cakes as you want. So all of a sudden, you've got this greater ability to use that oven. So instead of talking about CPUs, we could talk about culinary processing power. So if we think of that as the cluster, it also lets us do that, sort of the application remains that one-to-one connection for that licensing type environment. And lab maintenance becomes a lot easier in a lot of ways. Because now, and Mirko will talk about this a bit, you do one master image, you update that one master image, and with your ability to update the virtual images that you have, you just go swap them out. So you don't have to run Windows sus servers, you don't have to run updating, patching. You're doing it on one, and then you're updating everything. That allows for actually greater ability to test on the fly, because you just test that one. That also sort of moves away from the fact that, well, this lab has both laptops and desktops. Because the software, the operating system, is self-contained, the hardware is abstracted, you just need the one image. Right now, we need two images in there. So that's my little spiel. I'm going to turn it over to Mirko now. And we got a little skeleton there of a leopard, and it's the lab changing its spots. So swap this for you, Mirko. Your connection to the virtual.
Thank you. I hope all our virtual people can hear me all right. Okay. So here's the first slide again, in case you didn't catch it the first time. Right, so computer lab by day, SuperComputer by night. It's changed actually a little bit since we actually started working on the project in earnest, and it could probably now be titled Computer Lab all the time, SuperComputer all the time. We're gonna get to that though. Right, so going through the lab again, we've got optiplexes and we got the laptops. So the optiplexes have nice i7 4-core 8-thread processors and 8 gigs of RAM, and the laptops have 2-core processors with 4 threads and again 8 gigs of RAM. And I think everyone can agree that students generally don't need 8 gigs of RAM and 4 processors with 8 threads. So again, hopefully we can split this in half. And so what the plan is actually to wipe Windows out completely from the lab. We're going to install Linux on every single one of these computers, and it's actually going to be a server edition of Linux. So it's really stripped down. Then we're going to install Window Manager on there, and I'll get to that in a little bit. And we're going to throw VMs on there. And we're going to be able to throw whatever VMs on there we want. We don't just need Windows. But again, that's something I'm going to get to in a little bit. So what ends up happening is each of these VMs are only going to run half of the system's actual capabilities. And the other half of each of these systems is going to get clustered together into one supercomputer. And that supercomputer can also be controlled by the same server that's housing all the master nodes. And in this way, we actually end up, again, with a cluster and computers. And both can run completely independent of each other. They don't interact with each other. They both run all the time. So if we manage to pull this off, the cluster is going to end up with 120 cores. Yeah, that sounds right. 120 cores, because there's 60 of them, and each of them has 2 cores that we're going to be able to address. And remember, each of those cores has 2 threads, and so in the end, we're going to have 240 actual threaded processes that we can compile on the system. And then the whole system together is going to have 240 gigs of RAM, which isn't a whole lot in cluster standards, but we got 120 cores, so hey, don't need that much RAM. We actually need to keep the laptops out of the cluster, unfortunately. The laptops they don't have enough meat to really do clustering and do the VMs at the same time while running the Linux system in the background. So we had to kind of think of a different way to use the laptops. I'll touch on that a little bit later. So mostly it's just going to be the desktops that have the more processing power that are in the actual cluster. So really quickly touching on the virtual computers that are going to come out. So if you're actually using one of these computers, you're going to be in the virtual environment. You have 4 virtual cores, and virtual cores only need a thread. So you get 1 core per thread. They're single-threaded cores now. 4 gigs of RAM, and the laptops are going to have 3 virtual cores, leaving another one to kind of muck around and keep the OS going in the background. and 6 gigs of RAM, which hopefully kind of bolsters it a little bit for having less cores than the desktops do. So obviously we got a whole bunch of challenges to tackle before we can do this. So I'm going to run through this list, which isn't very exciting, but we're going to do it anyways. So the first thing is how to handle the UI. So the user interface is really important. We don't want users to be able to screw around in the actual Linux environment. We want them only to be able to mess around in the virtual machine. So we need a user interface that strips away all functionality completely while still providing a graphical interface that they can familiarize themselves with and not get too confused about. Which VM technology should we use? We've already picked one. I should mention that we're already pretty much done this whole system. We've solved almost all the issues so far. But yeah, so we had to pick a VM technology, and it needed to really work with the Linux system. It needed to work with the cluster management. It needed to work with everything. Obviously, we need to manage all these systems. So currently, we can just make GPOs and push them out and apply these to all 120 computers. We needed a new way to do this on the Linux system. Then we needed to figure out how to actually make a cluster. So I've worked with clusters before. I don't know how familiar anyone else here is with cluster computing, but I had no idea how the hell to make a cluster out of 120 computers. Then obviously we wanted to still integrate those laptops I mentioned earlier into some kind of useful way. And the big question here is, will we be able to do what we need with Windows? So by virtualizing these Windows environments, we might run into a lot of problems. But I'll touch on that a little bit later. But if we do manage to pull this off, the lab now gets multi-OS capability. So now we can boot into Windows, we can boot into Ubuntu, we can boot into CentOS, Chrome OS, whatever anybody wants, we can put VMs on these computers and update them individually. Obviously, this is huge. This is completely different than, as he mentioned, we make it, and for 6 months, this is how it has to stay. We can't change anything. So obviously, that's really good. It's a very adaptable system. We can replace the Windows OS. We can actually make new OSs or VMs specifically for exams, specifically for conferences that have specific software on them. We can do all kinds of really, really cool stuff with this now. And I actually, in case anyone was thinking this, I have had requests from profs to say, can we have a Linux lab? All we've got is a Windows lab. Because some of the profs in nanotechnology and some of them doing really high-level theoretical chemistry would prefer to be having a Linux lab as opposed to these Windows labs, which doesn't have the exact same tools. So another really great benefit of this is that it's going to be a low-cost alternative solution for research groups. So this cluster is going to be accessible by research groups. We haven't figured out how yet. Obviously, students take the first precedence since it is a machine. All these machines are dedicated for teaching. But if it's available, research groups will be able to use this. And so I know a lot of research groups need this kind of thing. I work very closely with research groups. That is my job. And a lot of them either have their own systems. A lot of them are decommissioning their systems because they're too big. It takes a lot of power to make a system with this many cores and a whole lot of space that not everyone has anymore as the school's getting more full. Right, and again, as I was mentioning before, we have availability for students. So there's a lot of profs who have master's students who end up using these clusters, and they have no idea how the hell to use the clusters. So I've talked to a couple of professors who were really, really hoping that when the system's available, they can actually teach courses on clustering because now they'll have clusters available to them to use. And of course, it would be really cool if this worked. So without further ado, I'm going to go into how we've solved most of these challenges so far and what technologies we've used. So hopefully you guys find this a little bit informative. So as for the user interface and virtualization, we're going to be using OpenBox and VirtualBox. So OpenBox is a window manager for Linux that is completely deconfigurable. We have neutered the front end of these Linux computers so that there are no keyboard commands at all. There's no Alt-Tab, there's no Alt-F4, Alt-F2. Anything you're expecting to be there doesn't work. When you're in the actual Linux environment, you're stuck. There's no taskbar, there's no nothing. You are just, all you can do is click a VM to start it, and once you're in the VM, you're stuck in the VM until you close it. There won't be two VMs running at the same time ever. Everything is locked down. And as for virtualization, we're going to be using VirtualBox, which, I don't know, maybe just because they both end in box was a good idea. But VirtualBox is really just my personal favorite VM manager. Everyone's got their own if they've been doing this kind of stuff. But I find it's really, really configurable. I can control individual VMs with very, very high precision. It supports full screen capability. So when you start up the VM, it's actually full screen. You don't know you're in a VM unless, obviously, you've been outside of the VM. And we have full USB compatibility so that you plug in a USB or 2 USBs or 4 USBs while the VM is running, they get ported directly to the VM. You don't need to worry about having clicking things and porting things over, it feels like you're in the system that you're virtualized in. So here is the very empty example of what the desktop's going to look like. And so like I said, there's nothing. We're going to have a desktop background. We're probably going to have some information on the background on what to do if you're confused by the fact that there's a whole bunch of icons. And then, of course, we're going to have an icon per VM. Now, the really cool thing about this is you can't even get into a file manager here. You can't open a terminal. You can't do anything. We have the home folder of these users locked down so that root owns them, actually. So you can't even move these icons. They are stuck. The really nice thing about this, though, is that we can move the icons. So if we want to, we can say, OK, for the next couple days, we don't want you to be able to boot into Ubuntu or Chrome OS or any other OS. We just take them off the desktop, and nobody can boot into them. We don't have to remove the machines. We just have to remove the icons. All right, so getting into controlling all these systems, so replacing our little GPO system that we had before, we are going to be using a tool called Saltstack. So Saltstack's a really cool program that you install on a master node and all of your minions. And what it allows you to do is, with really, really high granularity, pretty much do whatever you want on every single computer in your system. If you want to add a file to every computer, that's just one command. If you want to run a script on every single computer, that's just one command. We're mostly going to be using this to move around, not virtual machines, we'll get to that, but moving around configuration files, setting permissions, and most importantly, we can turn off virtual machines using Saltstack. We can say, any machine that's running Windows, turn off Windows. Any machine that's running this, turn off this. Salt actually allows you to select machines on a level of host name, how much RAM it has, how much RAM it's using, anything that's running on the machine. It is extremely granular. I can say every computer that has the letter P in its host name, turn off Windows on those ones. So this is really going to allow us to select by room. So if we actually decide to expand this idea to multiple rooms, we can actually select by room extremely easily with one command. And Salt is really, really easy to use. If you guys ever actually take a look at it, it's extremely configurable. It uses something called yet another markup language, which is based off of Python. That's extremely easy to use. You can just chain commands together and just run them on all your computers, and it's completely hassle-free. And it's also very, very, very scalable. You can use this on 2 computers. You can use it on 1 million computers. It's not going to choke on it. The next thing we need to talk about was image distribution. So anyone who's actually used virtual machines knows that the files that the virtual machine is contained in can get really, really big. This is an operating system contained in a single file. So we're expecting these to get sometimes close to 60 gigabytes for specifically the Windows one. The Linux ones will be a bit smaller. If we have a Chrome OS, it'll be a bit smaller. But the Windows one is going to be the real focus here. It's going to be huge. We need to get this on 120 computers as fast as possible. So the tool we selected for this is called Murder. Murder has been made by the Twitter team as a project to handle moving their big project files to everyone on the team really quickly. So what it does is it actually creates a private BitTorrent tracker and allows you to make a torrent out of a file, send that torrent to all the computers that need to download it, and start up your seeding and leeching and download stuff. And all the computers, as they download parts of this file, the other computers can download the parts that are complete per computer, which essentially means instead of having one big server serving one file to 120 machines, we have 120 computers serving files to 120 machines. We've tested it on a very small scale, and so far it works really, really well. We have, I think, 3 computers connected to the server, and it just flies. We have gigabit Ethernet between all of these computers, so we've managed to get the image that's currently 10 gigabytes out in just a couple minutes. So the way we're actually going to handle the VM distribution, we need to keep things so that there's minimal downtime. Obviously, the students are using these computers, or if someone's using these computers, we don't want them down for an hour while we transfer a 60 gigabyte file to 120 computers. So what we're actually going to be doing is hoping we have enough space, and we should, as long as we don't have 1 million VMs on these computers, we'll actually be able to have a cached version and a running version in the case that we're updating a VM. So what this allows us to do is edit the master VM, which has all your installations, has everything already configured. And all we have to do is push that into a cached area, start the BitTorrent, it's going to go, it's going to do its thing. Once it's done, we can have a pop-up come up and say, all right, we're shutting down your Windows VM in 5 minutes. That pop-up's going to stay there. Everyone can close their stuff, they can do whatever they want. After that goes down, we have Salt turn off every single Windows VM, and we move the cache copy with a simple move command. We're on Linux, it's quick, over top of the old one. Then another pop-up comes up and says, you're safe to use Windows again. and it's that easy. Downtime should be within the minutes, if that. It'll be really fast. So that takes care of most of everything that actually has to do with people using these computers as users. So the other end of this is the actual clustering system. So as I was saying before, I've worked with some groups that actually use clustered computers, and everyone seems to be using something called Torque. Torque is their cluster management system. So I went and tried to use Torque, and it works really good. So the way Torque works is you, again, like Salt, install something on your master, you install something on your minions, and the minions report to the master how big they are. It tells them how many nodes we have, how many CPUs we have, how much RAM we have, if it's being used, if it's up, if it's down. It reports a whole bunch of stuff to the master. And what the master has is something called a scheduler. So the scheduler, you submit a job to. You say, I want to run this command, and I want it to have 40 CPUs and 200 gigs of RAM, and I want it to run for 10 hours. The scheduler is going to find when that's available, and it's going to shove it up there, and it's going to distribute your job across all of these systems and run the job. And it's that easy. It really is. I was actually really surprised. Setting it up was a bit of a hassle, but once it was set up, it was really, really easy to get working. We haven't been able to do this, obviously, on a large scale yet. We've only got a couple systems that are ready and in this testing phase. So we've only got 8 different cores that we can run on. So there's not really too much of a difference that you can notice so far. There is a difference. We've done some compilation. We've done some other things with it. Hopefully, we'll be able to do much larger scale tests with this very soon. We also have a couple groups that have already volunteered to run their commands on this that need a cluster right now once it's ready. So if you get it in time, they'll be more than happy to give us some testing stuff. Right, so unfortunately, Torque does have a couple of limitations that I didn't really write here. The first thing is it doesn't know when to stop itself. If you tell Torque to run on node 5, 8 gigs of RAM, it's going to try to do it. It doesn't care if the node's only got 4 gigs of RAM. It'll try it. It'll fail, but it'll try it. The other thing is that if a job itself, because Torque doesn't know what the job is, it just knows that there is a job and it needs so much. If the job itself actually runs through the entirety of the RAM, it's going to choke. The computer's going to choke. It's going to run out of space. So we need to make sure we implement some kind of wall here to make sure that nobody's being able to do this, obviously, because everyone's using these as a user. This stuff's going on in the background. We want to make it so that nobody notices a difference. No computers get crashed or turned off. We have to make sure of that. The other thing is Torque doesn't really have a fallback if a node dies. If you turn off a node and Torque was running something on it, it doesn't know what the hell to do. It's just, okay, no, job canceled, we're done. So we need to make sure, because some of these jobs go for months. These users, I've seen jobs that have actually gone for months on these types of clusters. They are insane. So we need to make sure that these computers can't get turned off. Obviously, a power out is one thing. This isn't going to be a guarantee. This isn't a replacement for SharkNet. This isn't a replacement for any of these big, huge clustering things. So a power outage is going to screw them up. But we want to make sure users can't turn these off. And so one thing is we've already disabled that from the Linux perspective. We are hoping to disable this from a hardware perspective. We want to disable the power button on all these computers. That's users can't turn these off. We can still unplug them, but users can't turn them off. The one last problem that we have to address is that in order for Torque to work, you need a consistent file system across every single node. So what we need to do is mount something on these Linux systems in the same place on every single computer, which is actually where those laptops come back in. So while the laptops don't have enough CPU to be used in the cluster, they do have automatic built-in and really cheap power redundancy. So if power goes out, the laptops stay on. So hopefully what we can do is partition the laptop's hard drive, and we might even replace the laptop's hard drives with bigger hard drives just so that we can do this more efficiently. Partition it in half, and we can make a distributed file system on those partitions. And that distributed file system spans across all these computers, and it creates one big glob of memory. It's not quite as fast as having a big hard drive, but it's redundant. If something fails, if a computer goes down, the whole system's still okay, because one system goes down, the rest of the system can take care of what happened. And so the fact that the whole system will generally stay up in a power outage makes it so it's going to be way safer. And all we need to do is make sure that our network also doesn't go down in a power outage. But as Marcan mentioned before, we can actually segregate this lab from the rest of the system. So that's really good. So we haven't looked too much into distributed file systems. This is one part that we haven't actually fully figured out yet. But we've looked into them. There's things like MooseFS. There's a couple other ones, GlusterFS. They have a whole bunch of different ones that look like they're very, very valid. All of them have their pros and cons, but unfortunately I can't tell you about those today because there's still a couple details we need to work out. But that's pretty much all we need. So there's one last issue I want to talk about, and that is, of course, Windows, which always ends up being a problem. Right, so Windows likes to be unique. If you have a lab of 120 machines, each of those 120 machines has its own little personality. And if anyone here has actually run a lab, you know 3 of those machines are going to break in some weird, inexplicable way, even though nobody's touched them, and you don't know how to fix it, and you're going through the registry, or how the hell did this happen? We're making clones. These are going to be carbon copies of each other. If one breaks, they would all going to break the same time because they're all exactly the same. And if we fix them, we fix them all at the same time. We don't have to fix one at a time. They all work exactly the same. This is going to create problems, though. We can't have 120 computers connect to the Active Directory when they're identical. It's not going to work. Especially when we're replacing these VMs just every single night, it's not going to work. So we're actually going to be taking these off of our Active Directory system. Hopefully this is, again, miracleware or imaginationware, or whatever he called it. We need to be able to connect to users' profiles still without connecting to Active Directory. So now within Science, this is actually going to be possible because we kind of filter everything through a big NFS share anyways, so it's not going to be too difficult. But if everything goes well, we should have a system that you can sit down to. You're already logged in. If you start Windows, you don't need to log in. It's already there. If you want to access the internet and you want to access your personal files that aren't going to be disappeared as soon as you turn off the system or leave it for too long, you need to log in, and it's going to do all the mounting for you. So that's currently what the plan is. I don't know how we're going to execute that. I'm not going to lie to you, but we're going to try. Obviously, we're going to be running into licensing issues as well with these clone virtual machines. Not Windows licensing. We have a whole lot of licenses at Waterloo. We're not going to run out of licenses. No one's going to shoot us for having Windows VMs. But some software depends on MAC address. Some software depends on unique IDs that are built into Windows. They want unique GIDs. You got 10 of them running the same thing. They think something's going up, and they get all mad at you. So we are going to be running into issues with that. We know we are. Brace for impact, and go in, see what happens. Hopefully we'll be able to solve all that as it comes. But if we can get all that working, hey, we can fix everything by replacing the VM. Windows goes down, it's fixed. Really, really simple. And I really feel that if we do manage to pull this system off, we're going to have something really cool and really, really useful for everyone involved. So that's it. To be continued, we're going to actually try to implement this summer/fall, depending on how busy the lab is. We're going to be doing one row at a time, see how it goes. And if everything goes well, we'll see you hopefully next year and tell you how good it went. Or bad, if it went bad. But hopefully good. Are there any questions? Yeah.
How do you see the system working with software that requires hardware authentication, like those USB keys you put in, it authenticates the software?
Oh man, we don't actually use any of that right now. So far, there's nothing like that coming up. When that happens, that's going to be trouble. So again, there's going to be a lot of talking.
It shouldn't be trouble actually, because the hardware is still there.
It just recognizes the USB.
It just recognizes the USB.
If it does that, it would be
so it should actually work because it's just going to pass it through. So the Windows VM will launch. It'll say, "Oh, I have my key," because each is unique already.
Oh, yeah, I did say that it had USB pass-through working right now, so that part
So
I
that
guess
should
is
work.
taken care of. Yeah.
How do you authenticate your users if you don't have Active Directory?
So as I said before, the way our Nexus system is actually working right now, we have something going on where all our shares are going through NFS currently, aren't they? Alan's got some set up.
Yeah.
So we can actually hook these up through a different type of share. So hopefully we're going to have to make some front end. It's not going to be anything too complicated. It's going to be put in your credentials. It's just going to be a different pop-up than the Windows popping up. And once that's there, we'll just have an automatic mounting system. You don't need to be in the Active Directory. I currently have systems that work off of this that aren't in the Active Directory. You can still authenticate against the Active Directory. We may need to do some CAS stuff. We have CAS authentication on site. Is that standard? I don't actually know what CAS stands for.
I can't remember what CAS stands for. Anyway,
either way, we are going to, that's what I mean. We're going to have a lot of trouble with authentication. That's going to be our biggest hassle. Like we've solved all these other problems and Windows is going to be the one stuck pipe right now. Unfortunately, getting that working with everyone's
So
files.
the plan for the Windows VM is just that it's its own device. It actually is always on. So as soon as a student launches it, they can run anything there. What they can't access is anything that's on the network. So that's the part they have to authenticate to, and there are tools that will do that. We just have to figure out which one. So that's what we're going to do. And then part of that would be scripting that it mounts actually a home drive. And part of that then would be when that device is closed, it actually just refreshes back to a neutral state. So anything they personally download on there will be lost if they haven't saved it. So that's going to be part of the sort of the user training, but part of that will be just on the desktop, including things like make sure you save your files. One of the nice things about that, though, is that one of the complaints often from faculty members when they're teaching, the students walk in the first week, they actually can't get on the machines because they've forgotten their passwords. They've forgotten. So the teaching sessions for the first week are really rough. In this environment, they just walk in, they click, it's on. Whether they can save their files to a network share, not a big deal because they can always save them to USB.
Yeah, until the system works again, or until their user account works again. Anything else? Yeah.
If you didn't have that lab, if you didn't have all those machines and those laptops, would you set up a lab like that as opposed to say thin clients and a whole bunch of blades in the server room?
Honestly, I don't know. We did this because we have the lab. I still think a lab is a useful thing to have, as much as people are going with the, well, I guess if you have thin clients, it's pretty much the same deal. Exactly.
Everything's in the server room.
Yeah, exactly. Everything's up in the server room. Honestly, we're doing this because we have the lab right now.
And one of the reasons we still have this lab, because it was just refreshed, is because of the licensing. So this lab couldn't go away the last time we rebuilt to put the new hardware in because of that software limitation. As soon as we can virtualize that, yeah, that doesn't go away. We won't be doing this.
So,
unless this is really cool.
Then we might keep it.
What would make this really cool is less for a lab, I think, than to access all the machines in the offices. Imagine that how homogeneous the set of machines have to be.
They can be all over the place. Torque is pretty accepting with that kind of stuff. So yeah, that was one thing we were actually discussing, is whether or not we could do this on these machines, is because one thing he said, a VM doesn't need to worry about the hardware. They're all the same. You don't need a different image, or you don't need to install special drivers on different stuff. If it works, right? So, and again, users really don't know that they're in a VM if they're using the VM. It's pretty seamless. So one thing I was thinking about, which might be a bit of a stretch, is we could put the entire science faculty's computers into a supercomputer, if they're powerful enough, which would be really, really cool.
If they volunteered.
Oh, we wouldn't tell
They wouldn't have to know. They're users.
I'll tell.
We'll talk later.
Any other questions?
We've stunned you.
Yeah, sorry.
Yeah. Very interesting.
And nothing from the online world.
Nothing.
The virtualized world's talking about our virtualization.
Okay. Either that even very precise and very complete.
I hope so. I hope that's what it is.
Thank you very much.
Thank you guys.